Welcome to the Math Cafe, enough pie for two. I am Miss F.
And I'm Mrs. H. Hey, where's the pie?
Oh, the pie. We gotta work for the pie, I think, in this one.
What? No pie?
Yeah, not today.
That's disappointing.
But today, instead, we will be learning about circle geometry, and in particular, the tangent radius property.
That sounds like fun. So for today, you guys are going to need the worksheet supplied, a protractor, a ruler, and a pencil. Make sure you have those supplies handy.
And at any time in these videos, if you feel like you need to, just pause or start from the point that you need to look at again. You have that ability.
Wait a minute, they can mute us?
Yeah, kind of scary.
They can pause us? Good thing you don't have that ability in class.
Make sure you don't mute us too much, though. You still need to learn.
All right, I guess let's get started.
Awesome. So let's turn to your diagram of the circle with the center given and a point on the right.
Okay, so let's label the center. Let's label it O.
Perfect.
Okay, and we'll label the point to the right. Let's label it point A. Okay, what's next?
Okay, perfect. Next, let's draw a line that touches the circle only at the end point of the radius to the right point. Point on the right.
Whoops, you have to say that again. You're just basically say draw on a radius.
Oh, okay.
Yeah, right? So, start that again. It's really what you're saying is
Oh,
draw,
sorry,
draw
I
on a
skipped
radius from,
I
right?
skipped us.
I know.
Okay, so, okay, draw in your radius. Remember that goes from the center to any point on the outside of the circle.
Oh, okay. So, let's get a line here. So, we're going to draw a radius from point O to any point on the outside of the circle. What about right there?
Perfect.
Perfect.
Okay, next, let's draw a line that touches the circle only at the end point of that radius to the right point A.
Okay, so we're going to draw a line segment from point A to where the radius touches the outside of the circle. Okay, so we're going to draw it from here to there. And it's okay if I go past, but it's touching only at that point. Does that look good?
Good.
Perfect.
So, Miss H, this line you've drawn is called a tangent line.
Oh, okay, so let's label this line segment. Let's go this point A. Okay. So this is line segment AB, and we can say that AB is tangent to the circle.
Perfect.
Okay? What's next?
Now we need to measure with your protractor the angle formed between the tangent and the radius.
Okay, so we're going to measure this angle here. So the point where the radius touches the line segment, let's call that point C.
Perfect.
Okay, so we're measuring, you're telling me to measure angle OCA, or we could call it ACO, or we could even call it angle C, right? So we're measuring angle OCA. Okay, so let's grab that one here. Okay. Whoopsies. Okay, well, it looks to be, whoops, a little off there, pretty close to 90 degrees.
Perfect.
Okay.
Let's record that on your handout.
Oopsies. Sorry about that. Okay, so angle OCA is about 90 degrees. Okay, so what are we doing next?
Next, we're going to draw on this same circle another radius and tangent line, and we're going to measure that angle formed. So
Okay.
let's start by just drawing another radius.
Okay, so let's get another line. So we're going to draw another radius from center O, obviously, out to another point. Okay,
Perfect.
and now from the same point A, we're going to draw another tangent. Okay. Okay, and let's call this point point D.
Perfect.
And you're asking me to measure angle ADO.
Yes. Or ODA. Either way is okay.
Okay, so let's measure this again. Whoops, moving the line. Uh-oh. Okay, it's a little off. I know. Oh, actually that looks to be about 90 degrees again.
Perfect.
Okay.
Now we So, Miss H, what do we notice about the relationship between the radius and the tangent line?
Well, it looks like in each of our examples here that every time the tangent to the radius formed a 90-degree angle.
Perfect. And correct.
Okay, and so what else can we say about where the radius meets the tangent line?
Well, we can say it meets the tangent line at point D.
And what's that point called?
It's called the point of tangency.
Vocabulary, something else that you guys should be writing down in your vocab. Point of tangency. And so how should they define that?
So the point of tangency is exactly where, at the point where the radius and the tangent line meet up.
Perfect. And we know that that point always forms a 90-degree angle. So therefore, we can also say that the tangent line is perpendicular to the base, to the radius.
Good vocab use.
Perfect.
Okay, so vocab alert. So we're going to talk about the definition of a tangent line. A tangent line, in this case AB, is where it touches the circle at only one point, and it does not have to meet up with the radius. This could be drawn anywhere, as long as it goes through the circle once.
Perfect. Important to put that into your vocab.
To remember what we talked about.
All right, so let's now use what we've learned about the tangent radius property to solve a simple math problem. So say you're given a line segment and you've been told that it is tangent to the circle. How would you determine where the point of tangency is? Mrs. F?
So first of all, we know that from the tangent radius property that if our radius meets up with our tangent line, it makes a 90-degree angle.
Perfect.
Let's go backwards. What if we draw in a radius at a 90-degree angle? That should meet up with our tangent line.
Perfect. So let's draw it in. So what you would be doing is you would use a protractor and actually measure the angle. But, all right, there you go. Okay, so we are going to draw a line segment, a radius, and it should meet up the tangent line at a 90-degree angle. All right, so we would know that, we would want to check that that forms a 90 degree. Therefore, the point where it meets up with the tangent line, this would be your point of tangency. Correct?
Right.
Perfect.
So let's use what we learned about the tangent radius property in a real practice question. Okay, so in this question, we are determining the measure of angle ABO, knowing the tangent radius property.
Okay, perfect. So let's look at the information that this question is giving us. So right away, they're telling us that angle O has a measure of 63 degrees. And we're asked to solve two angles here. We're asked to solve the measure of angle OAB, so OAB, this angle, as well as angle ABO, so the two unknown angles. It appears that the line segment AB is tangent to the circle, right? Therefore, using the tangent radius property, we know that it is forming a 90-degree angle. So
It's where the radius and the tangent line meet up is their point of tangency, and that should be at a 90-degree angle.
Perfect. So we know that this is 90 degrees. How are we going to solve for the third unknown angle, Mrs. F?
Well, remember from video 1, we talked about the properties of triangles that we know. And in that case, we know that the sum of all three angles in a triangle equal out to 180. All right? So if we have two of the three already, we can just add these two together and then subtract them from 180, and that will give us our third angle, angle B.
Okay, so the two given angles now, so the 90 degrees using the tangent radius property plus 63 that was given to us, that's 153. If we subtract those from 180 degrees, we're left with
27 degrees.
27 degrees. Therefore, angle ABO is 27 degrees. So we've used the tangent radius property to solve for an unknown angle. Perfect.
Perfect. All right, so let's move on to practice question 2 and do something a little different. Let's determine the length of an unknown side of a right triangle knowing the tangent radius property.
Okay, so let's look at the information given here. So we're told that this is a right triangle, and we have two of the legs of the triangle labeled. So we have one side length of 20 centimeters, another side length of 15 centimeters, and it's asking us to solve the length of line segment CO, which they've labeled D. They've also told us that from the center out, we know that this is the radius, is forming a 90-degree angle with line segment DC. Therefore, we can say that DC is tangent to the radius. And now we've got a right triangle. So what theory are we going to use to solve for this unknown leg?
So anytime you see a right triangle, it's probably a good idea to consider something like Pythagorean. And in Pythagorean, we talk about the two smaller legs areas adding up to the hypotenuse area. So in that we get a squared plus b squared equals c squared, and c squared being our hypotenuse.
Okay, perfect. So now we can just substitute the given values into this formula and solve for the unknown leg. All right, so let's make our unknown leg d a. So that will be, b would be the second small leg of the triangle, so that would be the 15. And our hypotenuse, 20, is in c. Okay, so now what do we do?
So from here, we're going to want to simplify our equation and solve some of these squared values. So in this case, d squared stays the same. And 15 squared is 225.
And then 20 squared is 400. And so now we're going to use our strategy of solving equations by balancing to isolate the variable d by itself. So first step.
So to get d by itself, we have to make sure that 225 is off of this side. And to do that, we need to do the opposite of what's happening. It's being added, we need to subtract from both sides.
Okay, so we'll subtract 225 from both sides to keep it balanced. We're left with d squared on the left-hand side, and 400 take away 225 is 175. Okay, and our last step then in solving.
So because d is being squared, we need to do the opposite or the inverse of squaring something, which is square rooting.
Perfect, I remember that. So we're going to square root both sides, and we're left with d is equal to 13.23, approximately. That's been rounded. Perfect. So we've used the tangent radius property to solve for an unknown leg in a triangle.
As well as Pythagorean, because we have a right triangle. And with the right triangle, like I said, your rule of thumb, start looking for Pythagorean.
Perfect.
All right, so for the last question, practice question 3, we're going to actually apply the tangent radius property to solve a real world problem.
What? Math applies to the real world?
I know, it's pretty crazy,
oh,
right?
We better do this one. All right.
Okay, so Miss Huckluck, late for the math cafe.
I'm never late.
She's always late. She decides that she's going to take an airplane because the traffic's brutal and she doesn't want to drive.
Seems logical.
Yeah. So she drives an airplane, or flies an airplane, and she's cruising at an altitude of 9,000 meters. She knows that the cross-section of Earth is a circle with radius approximately 6,400 kilometers.
I do know that.
Yeah, it's pretty bright. She's also wondering how far she is from point H on the horizon that she sees outside her window. So she wants to be able to calculate this distance to the nearest kilometer. Why don't we help her out?
Okay, so let's look at this a little closer here. All right, so here's the information that's been given in a picture. All right, so we know that the radius of the Earth is 6,400 kilometers. We also know that I'm flying at an altitude of 9,000 meters. I think actually before we move on here, we've got different units of measurement. We should simplify by putting them in the same units.
Agreed, because you can't work with measurements that aren't in the same units.
So let's change 9,000 meters into kilometers. And so 9,000 meters would be 9 kilometers.
We just divide by 1,000, which is the conversion.
Perfect. Okay, so the question is asking us to solve for the distance from point A to point H. This is the airplane, and H is the point on the horizon. And so what else can we do here?
All right, so we know the radius here is 6,400 kilometers. So is there something else that we could draw in that would help us match up these points?
Well, let's draw in another radius, right? We know that from the center of any circle to an outside point is called the radius. So I'm going to draw in a radius from here to point H.
And if these are both radius, then we should know that this also is 6,400 kilometers.
Okay, so I'm going to label that in 6,400. And because I've drawn a radius to point H, I know that line segment AH is a tangent to the radius. Therefore, I can draw in the angle formed between the tangent and the radius at 90 degrees. We learned that.
From the tangent radius property.
Perfect. So now I guess, what are we going to use to solve for line segment AH?
Notice again that we have a right triangle going on here, and that means that we can use, you got it, Pythagorean.
All right, so we're going to use the formula again. A squared plus B squared equals C squared. And are we solving for the hypotenuse or for a shorter leg in this one?
This one we're given the hypotenuse, so instead of adding the areas together, we're going to want to subtract them.
Okay, so we're solving for x. I'll substitute the variable x into a here. The other short side of the triangle would be the 6,400 kilometers. And the long side would be these two line segments joined together, so 6,400 plus 9
All the way from A to the center.
would be 6,409. You might want to get your calculators out for this one. We're going to be dealing with some fairly large numbers here. All right, so we know that x squared is just going to be x squared. And Mrs. F is helping with the calculator here. 6,400 squared is?
It's 4096 and then 4 zeros.
So it is 40,960,000. And then 6,409 squared would be? We'll just take a second here.
It'll be 410,75281.
All right, so 41,075,281. All right, and now we're going to solve simply by balancing again. So we need to subtract the 40,960,000 from both sides to isolate the variable x by itself. And when we do that, all right, we're left with x squared is equal to?
115,281.
All right, and the last step, like you said in the last example in any Pythagorean theorem, we don't want x squared. We have to do the opposite or inverse operation. We're going to square root both sides for an answer of x equals,
339.53.
and this is in kilometers, right?
Also remember from the question, it asked us to round to the nearest kilometer. So Miss H doesn't like to deal in decimals when she's flying her airplane. She's got a lot on her mind. So we need to round. And because there's a 5 behind our 9, which is where we're rounding up to, we need to round up to 340 kilometers.
Okay, so this would be 340 kilometers following proper rounding rules.
That's our length for x here.
Good job.
Nice. We got it. Hey, wow, those teachers seem really great. Look what you learned today.
Hey, that was us.
Oh, right. Awkward.
Awesome. All right.
So let's summarize what we learned about today.
Okay, so let's talk about the tangent radius property. So we learned basically two things. So a tangent to a circle is a line that intersects the circle at only one point, right? And a tangent to a circle is a line that is perpendicular to the radius at the point of tangency.
Wow, sounds fancy. You guys learned a lot today.
Pretty good.
Yeah. So stay tuned for our next episode where we talk about chord properties and maybe,
Just maybe, there might be some bloopers at the end of this video.
Yeah.
Just maybe.
enjoy.
Have a good one.
Welcome to Enough Pie for Tea. Oh, no, that's wrong.
Math
Don't yell,
yesterday.
don't yell
Take
either,
two.
just.
Am I yelling?
Teacher voice, a
I
little bit.
totally do that.
She yells.
I'm a yeller.
She yells.
I do it in class. I am a yeller. I'm a projector.
Alright. Okay, so if we have a 90-degree angle, and we determine that angle using the tangent radius property, we add it to the angle given, 63 degrees, that gives us a total of 157 degrees. And so like you said, now we will subtract 157.
degrees.
Sorry?
153 degrees.
Oh! Redo! You're not even in the picture.
Awkward. Let's zoom out a little bit.